Hey guys, welcome back to my YouTube channel. So we are continuing the discussion on the digital electronics. So actually in the number system itself I thought to teach this one, but I forgot on how to say about this gray code. So let me say this and let's continue on the K-Map things. So gray code is a unit distance code. So this is one of the important coding scheme. It's an unit distance code. So like in K-Map we have used, right? So there will be only one bit change in the K-Map diagram we represent. So similar to that, it also will be there only one bit change. So which is an unit distance code and code which exhibit unit distance, like only one bit changes between successive numbers. So let's see how we can convert from binary to gray. So here is a conversion from binary to gray code. So binary to gray code. So we can convert the binary to gray code is the GI, which is the bit in the gray code. So which can be find out by the binary input ith position, which is XORed to binary inputs I plus 1th position, means next position. Okay, so this is how we usually calculate the thing. So for an example, let's take an example. So binary code which is 1011. Okay, so this is gray code. So how we can find the gray code is so GI, which will be equal to BI if MSB. So last bit is represented as it is. So if it is MSB, so this conversion is else. Okay, so this first bit will be always represented as it is 1. Then this BI, for the GI to be found out, the BI need to be XORed with the next output. So this will be XORed with this one. So 1 XOR 0, which will be written as what, which is 1. So then this 0 is XORed with 1. So that will be giving 1. So then 1 is XORed with 1. So that is 0. So this is how the gray code representation for this one respectively. Okay, so this is very simple. So let's see in reverse process, like gray to binary. So how we can convert from gray to binary is the same thing. So binary ith position, which will be same as it is if MSB. Okay. So next binary positions will be find out by GI, which is XORed with BI plus 1. Okay, so BI plus 1, which is XOR. So how we can get the binary code from the gray code? So let's take this as an example. So this bit will come as it is, so 1. So we need to XOR this with X. So 1 XOR 1 is 0. So then 0 XOR with the 1, that is also 1. Then this will be XOR with 1. So that is 1. So here you can see this both seems to be same. So this is how we could convert from binary to gray and then gray to binary. So this is binary to gray and this is gray to binary. Okay. So this is on. So here we'll do XOR. So let me write it here. This is XOR. So both will do XOR operation only. So this will also XOR. So we need to know from where to do XOR. So when we converting to binary, the bits in the binary itself will be XOR. But when converting back to binary from gray, then the binary bit is XORed with the gray code, next gray code. So that is what we have mentioned here. Okay. So I hope this is understood for you guys. So from this I am closing this one. So this is one of the unit distance code. So this is one of the very important thing. Maybe in many of the interviews they have they may ask these kind of direct questions in things. So let us continue our discussion on the things. Like we have seen up to 5 variable K-maps, right? So let us continue the thing. So prime implicant, essential prime implicant. So many concepts are there to discuss. So let me start with the implicants, how to find those things. So implicants is nothing but, so these are some terms. In examination, they may directly ask us to calculate the number of implicants, number of prime implicants and essential prime implicants. They may ask. So while I was studying college, these are some 8-mark questions they used to ask. So it is nothing but min term or max term. So this is number of min term or max term. Okay, so this is same like min term or max term. So prime implicant. So this is quite important. So this is after finding a group. So we will be grouping that together, right? So in order to minimize the logic. So after grouping, we will be noting that. So it is formed by combining maximum possible adjacent cells. Formed by combining maximum possible adjacent cells. Okay. So essential prime implicant. So this is quite confusing. So please listen to the definition carefully. So essential prime implicant. So definitions may confuse, but when we saw some example, it will be very good understood for you guys. So the essential prime implicant, the definition is that, so it is a prime implicant, but which contain at least one minterm which cannot be covered by other prime implicants. So listen to this carefully. It's a prime implicant. I am mentioning as PI. So it's a prime implicant which contains at least one minterm or max term, at least one. I am mentioning as M0 or M0. I am mentioning like MI. Let me represent as MI. So one minterm or one max term which cannot be covered by any other prime implicant, which cannot be covered by any other prime implicant, that is PI. Okay, so this is one very important thing. So let me give one example so that you guys can understand it carefully. So let me take a 3 input K-Map. So let me take two things. Okay. So the thing is that we are going to find out all the things. So let's take an example 1 1 1 1 1. So here it is 1 1 1 1 1, right? So this is the thing. So let me map it. So here the thing, this can be mapped like this, this can be mapped like this can be mapped like this. The thing is that, so here everything, how many how many implicants is that? So let me first write implicants. So implicant is 1 2 3 4 5. So number of minterm max steps. So that is what the implicant. So prime implicant. So prime implicant is a thing, that number of grouping. So 1 2 3. So there is 3 prime implicants. Essential prime implicant, which is the case where a min term which is covered at least only once and which cannot be covered by any other term. So here you see, let me differentiate it. So this min term is right. So this is only covered by this one. So which cannot be covered by any other thing, right? But this one can be covered in this and can also be covered in this. This one can be covered in this, we can also cover in this one. Okay. So this one is covered only here. So there is two essential prime implicant present here. So which is this one. So this one is only covered in this one and this one is also covered only in this one. So this is how we can say. So this is an prime implicant, so which cannot be covered by any other things. So that can be covered only once, means it cannot be covered by any other kind of prime implicants. So that is what we will be generally mentioning it. So here it has two prime implicants. So that is what the concept. So I hope you guys able to understand it, right? So this is how. So here if you see the prime implicant, even we can state this one also as a prime implicant. So here this grouping, right? So this one we can also include that. So there is a 4 prime implicant, but we can see only 2 essential prime implicants. So that is this one. So this element and this element. Okay, because this min term which is covered only in one thing. So there is only one group is forming. So we cannot cover this one with any other essential any other prime implicants. So that is why we generally state it. So this is one of the best example to cover it. So let me take some other examples like how to take it. So let me use any other K maps. So this is let me rewrite it because it is same, right? So let me add one here. Okay, so now you guys try to solve it. So please pause the video and try to solve this and let me know how many prime implicants and how many essential prime implicants that can be formed here. So let me please pause the video and try to answer it here. So let me draw the thing. So implicants, it's there is 6 implicants. So let me draw a grouping. So this is one grouping that we can do. So this is one grouping that we can do. So here one grouping that we can do. So here one grouping, here one grouping, and here one grouping. So let me name it. So this one 1, 2, 3, 4, 5, 6, 6. So there is 6 prime implicants that can be formed here. Okay. If we see what is the essential prime implicant, so here is an interesting fact that we want to take care. So let we go by each minterms. So this minterm can be covered by 2. So this minterm can also be covered by 2. This one is also covered by 2. So this can also be covered by, this can also be. So everything is covered by twice. So there is no essential prime implicant. So this is the prime important concept. So if you see, by adding just a one minterm to this function, we here can clearly see that there is no essential prime implicants that is happening. Because the thing that the each minterm can be covered by 2 prime implicants, means 2 grouping can be formed here. So I hope you guys able to understand this concept, right? So this is one of the very important concept. Please make a note of it, guys. So you guys cannot ignore it, because many of the things they will ask in the questions. Okay, so this is one of the key thing. So let's take another one example here. So I think this is hope fine. Let's take a don't care condition. Okay, so don't care condition is the logic. So we have seen a minterm and maxterm whether the output can be represented in 1 or 0, right? But here the don't care condition will come whether this can be 0 or it can be 1. So in this case that will be represented as x. The function will won't consider this as a some supporting or affecting term. Whatever may be the input here, the function will behave as it is. So these kind of logics can be written with a term of x. So we can if we need it, we can take that as a thing to include it. If we don't need, we can ignore it. So let me draw one example so that you can able to understand. So let me take a 4 input K-map. So let me draw it. So these kind of don't care condition, in many of the cases the input may be affected or may not be affected. Even if it is affected or not affected, the output logic will not be taken into account here. So that the particular function or particular performance that we are doing won't be depend on that particular input. So that is what the thing we have to take into account. So here a b c d. So the function which is given as a comma b comma c comma d, so which is equal to the summation of m 0 comma 1 plus, here they will give us don't care, so d. So they are giving don't care as 8 comma 9 comma 10 comma 11 comma 12 comma 13 comma 14 comma 15. So everything is there giving us don't care. So let me draw it in a K-map. So 0 0 0 1 1 1 1 0. So 0 0 0 1 1 1 1 0. Okay. So the prime implicants here coming is only 0 and 1. So this only marked as 1. Okay. So the don't care condition is starting from 8. So I think 8 is from here. I think 1 2 3 4 5 6 7 8. So 7 8 9 10 11 12 13 14 and 15. So everything is coming as don't care. So here the grouping can be done in 2 possibilities. So one is you can directly group like this and you can write a function. So f is equal to, what is this? So here it is constant, right? So a bar, b bar, and here it is c bar. So this one you can directly write it. There is another one option that you can do. Include this one. So here 4 bit is included. Then f will be equal to, here if you see b bar is constant, b bar, c bar. So if you think which one is correct, d is the correct. Sorry, b, c, the second one with the blue is correct. So this one is wrong. Because we have already clearly set the condition that we have to form the grouping with only maximum possibilities. So here the 4 grouping is possible. Then why we need to go for 2? So as it is don't care, the x can be 0 or 1. But if they are given as don't care, in the grouping we have to consider that as a priority. But you may ask a question. So why can't we group this one and add to this function? You may add it. Even if you add this one, so what will come? This will come as a and this one, the entire series of things, right? So which will come as here. This both. So this one eight grouping. So 8 grouping will come as only one. So this is a. So that is not needed because this is don't care. So even if you include in a function or don't include, that won't affect your system. If it is whatever may be the thing, as they mentioned, this is a don't care. So we no need to take into account. So that's we will be ignoring that. But for grouping purpose, we can ignore with other main terms. So this is one quite interesting term that you have to note about don't care condition. So I hope you guys able to understand the things, right? So in next lecture, I will be giving one more problems, like a few problems that we can do, and we can conclude our discussion on the K-Map. And then we will be starting with the discussion on the combination circuit. That will be quite more interesting. So stay tuned guys, like, share and subscribe the channel. So please motivate and subscribe the channels to post more videos like this. Thank you.